Friends, topic of today's talk is transmission impairments. In our previous classes, we have seen that the signal that is introduced in the medium from the transmitter is not received in the same form at the receiving end. Let's see, you have your transmitter T, here is your medium, and signal that is introduced here is S, and the signal that is coming out from the medium is, say, S dash. This is your receiver. Now, these two signals are different because of different impairments that is introduced by the channel or by the medium. We have already discussed different types of medium, and we have seen what kind of distortion or impairments introduced by them. We shall discuss these various types of impairments in detail in this lecture. First of all, let me point out, in case of analog signal, these impairments causes modification of the signal in different ways, leading to degradation in the quality of the signal. On the other hand, for digital signal, some of the bits which were sent as 1 becomes 0, and some of the bits which were sent as 0 becomes 1. As a consequence, bit error occurs, or the data that you receive is different from the transmitting end. Let us see what are the different impairments or common impairments. First of all, attenuation, and attenuation distortion. Second is delay distortion. And third is noise. We shall consider these three types of impairments one after the other. First of all, let us consider attenuation. While discussing about the transmission media, we have seen that for guided media, the attenuation is logarithmic in nature. Logarithmic for guided media. On the other hand, for unguided media, it is proportional to d square for unguided media. What is the effect of this? What happens because of this attenuation that is taking place? First of all, signal strength falls off as distance increases, and as a result, at the receiving end, it may not be possible to reconstruct the original signal. Second thing, that means it may not be possible to detect the data. That means what was supposed to be 1 has to be detected as 1, what was supposed to be 0 has to be detected as 0. That may not happen. Second thing is, because of noise, your signal strength should be above, much above the noise level. Otherwise, the signal will get submerged in the noise. That means the it should be above noise level. So, what is the solution for these two problems? How you can overcome this attenuation problem? One possible way to overcome this problem is to introduce repeater. Let us assume this is the medium, signal is introduced here. What you can do, you can put a repeater in between, which will boost up the signal strength and which will receive it, boost it up and retransmit. As a consequence, the signal that you get at the other end is of higher strength, and this repeater spacing will depend on what is the nature of signal, analog or digital, what kind of attenuation that is taking place. We have already mentioned in my previous lectures that this repeater spacing varies from 1 to several kilometers depending on the medium and the signal type. But another problem which we can call as attenuation distortion. This attenuation distortion arises because the attenuation of the signal depends on the frequency. That means attenuation depends on frequency. For example, let us consider the typical telephone lease line, which gives you a bandwidth of 3100 hertz, and it is 0, so 500, 1000, 1500, 2000, 2500, 3000 and say 3500. And on this side, let us draw, this is, let us assume 0 dB, this is in dB in this side, this is say minus 5 dB, this is plus 5, and here say plus 10. And let's do it with respect to 1000 hertz. That means for 1000 hertz the attenuation is 0, and for other signals the attenuation is considered with respect to 1000 hertz. So the nature of attenuation will be like this. It is at 1000 it is 0, and then it sharply increases. So you see the attenuation is highly dependent on the frequency. This introduces what is known as delay distortion. You may ask, what will happen in this particular case? As you know from your knowledge of Fourier analysis or the frequency domain representation of the signal, any signal comprises of different frequency components. what happens? The higher frequency component will be attenuated more than the lower frequency components. So, if you are sending a voice, say of Lata Mangeshkar's voice, which contains higher frequency components, that file will get attenuated, and at the receiving end you may not be able to recognize the voice of Lata Mangeshkar. So, the quality of the signal will suffer. Of course, this delay distortion is not prominent, this attenuation distortion is not prominent in case of digital signal, because the signal strength is limited over a small frequency spectrum centered around the data rate, and as a consequence the attenuation distortion is not predominant in case of digital signal. Now, what will you do in case of analog signal? When you are sending voice where the frequency component varies from 500 to say 3400 hertz, and the characteristics is like this. What can be done? You can introduce a what is known as equalizer. Which will nullify the characteristics of the channel. So, you can modify the signal characteristics, combine, that means channel plus equalizer together, and it can be made like this. Somewhat like this. So, this is with equalizer and this is without equalizer. That means what you are doing here, here is your transmitter, here is your channel or medium, then you are putting an equalizer before you are applying the signal to the receiver, and you can assume that these two together is acting as a medium, or you may include this equalizer as part of the receiver. That means the received signal will be equalized in this form, and at this end you will get whatever you have sent. So, this is how you can overcome the problem of this distortion introduced by different types of different attenuation of different frequency components. Let us consider the case of delay distortion. What happens? Different frequency components of a signal suffer different amounts of delay as it passes through the medium, and this is particularly peculiar to guided media. This is not encountered in unguided media. In guided media, this delay distortion is very predominant, and this arises because velocity of a particular frequency component is different from frequency, or rather frequency, the velocity varies with frequency. Velocity of the signal of the signal varies with frequency. Now, how do you overcome it? First of all, let us draw the characteristics again for the voice grade lease line. Here it is 0, say 500, this is 1500, this is 2500, and this is say 3500. On this side, the 1000, 2000 in hertz, 3000, and say 4000, different frequency components. It has been found that the velocity is maximum in the around the center of the band, frequency band. That means here it is the delay. Delay is more in the lower frequency side and as well as in the higher frequency side. This is typical of band limited channel characteristics. So band limited means your frequency band starts from 500 to 3400, and in this case, as you can see, the delay is more in the lower frequencies, it is also more in the higher frequencies. If you look from other side, velocity is more for in the center range and less in other ranges. Here also what you can do, you can use an equalizer. Using an equalizer, this delay distortion can be overcome. And using the equalizer, the characteristics can be like this. Sorry, it will be somewhat like this. So this particular signal without equalizer, and this one is with equalizer. Equalizer is nothing but some kind of filter, can be implemented by using passive components like R and C, or by using active components like operational amplifiers and RC, resistors and capacitors. This delay distortion is very important for digital signals. We have seen that attenuation distortion is important for analog signals and delay distortion is important for digital signals. What happens in case of delay distortion? Suppose you are sending a signal like this. Digital signal like this. Now, because the different frequency component has different delays, the signal component, higher order signal component will have more delay than the lower frequency component. So the higher order frequency components of this particular bit will fall on this particular bit as the distance increases, and this will lead to what is known as inter-symbol interference. This inter-symbol interference is very common in your for digital signals, and that is because of delay distortion. And as I have told, this can be overcome by using suitable equalizer. Let us now consider the third factor, the noise. We have considered attenuation and attenuation distortion and delay distortion. Let us now consider noise. The noise can be broadly divided into 4 types. The 4 types are thermal noise, second is intermodulation noise, third is crosstalk, and fourth is impulse noise. And let us start with the first one, the thermal noise. Thermal noise arises because of agitation of the electrons inside the material. As the temperature increases, the electron gets more agitated and that generates noise. One typical characteristics of this thermal noise is it is independent of frequency. Noise level does not change with frequency. That is why it is also called white noise. White noise means it is the with frequency the noise level does not change. It is uniformly distributed over the entire spectrum. Now, the equation can be written as N0 is equal to K and T, where N0 is equal to noise power density in watts per hertz, that is the unit, and K, as you know, is Boltzmann's constant, and T is temperature in Kelvin. Now, noise present in a bandwidth W can be written as N is equal to W K into T, and you can express it, this is in watts per hertz. You can express it in decibel, and then it becomes in dB it becomes equal to log 10 log K plus 10 log T plus 10 log K, T and W, the bandwidth. So, this is how you can express it in decibel as well. Let us consider the second form of noise, that is intermodulation noise. As you are sending different frequencies through a medium, say you are sending F1 and you are sending another frequency F2, what can happen because of nonlinearity? In the transmitter, in the medium, or even in the receiver. It can happen in all the three places. Because of this nonlinearity, it will generate frequency components F1 plus F2. And this F1 plus F2, suppose you are sending 100 hertz and you are also sending 300 hertz. So, these two will combine together because of nonlinearity and produce signal of some signal of 400 hertz, but your original signal may have a frequency component of 400 hertz. So, this noise components which is generated because of intermodulation noise will combine with the original signal, and obviously it will distort it. So that's how the intermodulation noise is generated. And obviously there is no straightforward solution. Only way to overcome this problem is to design the transmitter receiver in such a way that there is no nonlinearity. But your amplifier and other devices will have some amount of nonlinearity, and that will lead to intermodulation noise. Let's now come to the third type, the crosstalk. We have seen that when you are sending a number of transmission media and bunch them together as you do in twisted pair of wire, then there is some mutual interference. That means signal passing through one pair of cable will induce some signal in another pair. It is a common experience to listen conversation of other people while talking over telephone, and this is known as crosstalk. And obviously the crosstalk can be avoided by proper shielding. I have already discussed in my previous lecture that there are two types of twisted pair of wire. One is unshielded twisted pair of wire, another is shielded twisted pair of wire. So you have to use shielded twisted pair of wire to reduce this crosstalk. Finally, let us come to impulse noise. The other types of noises like thermal noise, intermodulation noise, crosstalk, these are measurable quantities depending on the medium that you are using, depending on the temperature, ambient temperature, depending on the nonlinearity that is present in the system, you can find out the amount of noise that will be introduced. But this impulse noise is really random in nature. It arises because of different types of random events like lightning, or say spark, electrical spark. And obviously when and how this type of noise will be generated is completely unknown. Say, let us see what is the effect of this type of noise. What happens in case of analog signal? Suppose you are talking and analog signal is communicated through telephone line. In case of analog signal, the effect of impulse noise is very negligible. Say a very small fraction of voice, if you don't hear, it does not really matter. You can still find out the what the person at the other end talking. You can make out that. But if it is digital signal, then this impulse noise really makes significant effect. For example, a number of bit positions, zeros will become 1 and 1 will become 0, and that will introduce errors in your digital signal. So we can say that impulse noise significantly affects the digital signal rather than analog signal. So friends, we have discussed different types of noises, different types of impairments that is introduced by channel or the transmission medium, and also different types of, there are two things. First of all, there are impairments due to limitation of transmission media. And second thing is some noises are introduced into it. So, in a practical real life communication media, these two will restrict the maximum data rate that you can send through a transmission media. Question is how these impairments restricts yourself so far as the data rate is concerned. That can be expressed by quantity, what is known as channel capacity. What is channel capacity? Channel capacity is the rate at which data can be sent under given constraints, given conditions, you can say. Given conditions means these are these impairments, noise and impairments. So, in presence of impairments and noise, what is the data rate that you can send? That is called channel capacity. And in this context, there are 4 parameters: data rate, bandwidth, noise, and finally the error rate are relevant. Let us see what do we mean by channel capacity. Obviously, we want higher bandwidth because higher bandwidth provides you higher data rate. But higher bandwidth means higher cost. So, what is our objective? We want to utilize the bandwidth to the maximal possible extent by suitable technique. That means, given a bandwidth W, we want to achieve maximum data rate. Let us see what are the constraints and what are the parameters which affects it. First of all, there is a Nyquist criteria according to which if the bandwidth is W, then maximum data rate max is equal to 2W. That means this is the channel capacity. When you are sending 2 levels of signals, that means you are sending binary data, binary signal, binary data. So, for a binary signal with 2 levels 0 or 1, high or low, the channel capacity is 2W. It is possible to increase the channel capacity by increasing the number of levels. Let us assume the number of levels is made H. For number of levels of 8 which is used in some of the practical lines, then the value of C will become 2W log 2 M. So, for W is equal to 3100 Hz, C is equal to, if you substitute this figure here, you get 18,600 pods per second. So, you see you are able to achieve higher data rate even for the bandwidth of 3100 Hz of bandwidth. That is possible because of suitable use of number of levels, and that is called encoding, and which we shall discuss in detail later on. Now, let us see the relationship between channel capacity with the relationship between data rate, noise, and error rate. What is most important is the ratio of the signal to noise, which is called signal to noise ratio. In dB, it can be expressed as 10 log signal power by noise power. And according to Shannon's formula, one of the scientists, the bandwidth, the channel capacity is related by this C is equal to W into log 2 1 plus S by N. If you assume that S by N is equal to 1000, then C is equal to 3100 into log 2 10,001, and that is equal to 30,894. This 30,894 is the maximum upper limit or you can say this is error free rate. Because here we have taken into consideration only the white noise, we have not taken into consideration the impulse noise and other types of noises. In presence of other types of noises, this maximum upper limit cannot be achieved. Also, we assume that we shall be able to devise suitable encoding technique to achieve this maximum upper limit, but in practice that is not so. Say, let us consider the actual situation, and this efficiency can be considered as C by W. What is the channel capacity and what is the bandwidth? And this can be expressed as 0, 2, 4, 6, and say 8 and 10. On this side, the hertz 10, 100, 1000, then your 10,000. If this is the theoretical upper limit of C by W, which you can call as efficiency, in practice it has been found that you can achieve only this much less than the theoretical possible limit. So, in practice, for telephone line. So, we can see that we have obtained the channel capacity possible in real life situations where there will be noise, there will be bit errors, and we shall not be able to devise suitable encoding scheme. So, friends, let me conclude this lecture by telling that in this lecture we have considered different types of impairments that happens as you transmit through a transmission media. As the signal passes through a transmission media, the impairments can be attenuation and attenuation distortion, which can be overcome by using repeaters and equalizers. There can be problem of delay distortion, which can also be overcome by using equalizer. Finally, we have seen different types of noises that is being introduced, and even in presence of noise, what kind of baud rate or data rate, I have not yet introduced baud rate, data rate that is possible even in presence of noise for a given bandwidth. Thank you.